All right, we can get started. Amy will continue her lectures on Lattice QCD.
Perfect. All right. How's everybody doing today? All right, you guys are doomed. My notes are getting, if you guys can see, this is what we're covering today. So please keep me honest. I will mess up so many minus signs today. All right. So I finally made it to one of Sebastian's lectures, and I liked his starting off with what did we do in the last episode. So here we go. This is what we did. We derived this guy. So today, we're going to talk about what do we do with this thing, right? So we discretized our action. We know in field theory, if we have an action, we can write down Feynman rules and draw diagrams and calculate them. That's not what we do in Lattice, though. We don't calculate diagrams because that's perturbation theory. So what do we do with it? We have to do something non-perturbative. We have to calculate the entire partition function. So our starting point if we were doing StatMech, the thing that has all the information about the theory is the partition function. So you trace overall states, and the weight of each state, or the probability that each state contributes, depends on the energy and the temperature, or the inverse temperature. So the equivalent for a field theory, we're going to do the same thing. We're going to trace over all possible states. But here, our fields are the things that encompass the states. So we're going to integrate over all possible fields. Right, so this is what we mean by a path integral. And I'm not going to define this formally because we're not going to actually do a path integral in the end. The beauty of the lattice is that it doesn't make us think about what this complicated object where I'm integrating over all spaces of functions is. All right, so I'm summing over states, and I'm weighting them by the Euclidean action where I have e to the minus action because I'm in Euclidean space, so that's taking time to imaginary time. And so that gives me just an ordinary exponential with a function up here. So it looks a lot like this. It actually is exactly this. So you can think of a Euclidean field theory. So a 4-dimensional Euclidean field theory is the same as a 3-dimensional statistical mechanics system where the temperature, this goes like, what, 1 over t. So the time, Euclidean time, acts like an inverse temperature. So we're in Euclidean space. This means time is not a real dynamical thing that we have at our disposal. So the things that we can calculate are going to be limited to certain types of observables. For example, things that don't depend on time, like masses, spectra. Those are time-independent things. We can get them by looking at the partition function in, say, the 0 temperature limit or the long time limit. That gives us the ground state. I'll talk about that next time. if we want to look at dynamical processes like scattering, you have to be a little more clever, and Andrew is going to tell us all about how to do that. All right, so complicated thing. I don't want to derive it formally. I am not a super formal person. I learned it at some point and then forgot it quickly. But the lattice makes it easy on us. So what happens when we discretize our function psi of x, our fields? Psi of x just goes to psi sub x. So I have a value of psi, and I have a different value, say, at every point on my lattice. So I can think of this as just being a vector of size, where the vector index runs over how many lattice sites do I have. All right, so I guess technically when you are doing field theory, you'd be integrating over your A's, but I wrote U's because in lattice we're going to do U's. So our A of x goes to a link variable, and we have a link that's associated with some position, either the starting point, the ending point, the midpoint, however you want to define it. And it also has to have a direction. It points in a certain direction. Okay, so now that I've done this, I've just turned continuous functions into vectors. If I want to integrate over all possible values of my fields, if I'm just picking one point on my lattice, I have some field psi that lives here, and I just have to integrate over all possible values of psi at that point. That's just a regular integral, right? Psi has some range, minus infinity to infinity, and I just integrate over all possible values here, but I have to do that at every point in my lattice. So this path integral, this funny formal thing that I don't want to have to define, just becomes integrating over every site, and I just have to do it for all of them. So this takes a path integral and turns it into an ordinary integral, but what's the dimension of this integral? If this is my lattice, what's the dimension of my integral? Nine. Why? 9 dots? Yeah. I have a different psi at every point on my lattice, and here I drew 9 points. So this would be a 9-dimensional integral. In real lattice calculations, we have more than 9 points. We have a lot of points. So this is a very, very high-dimensional integral. Fortunately, we have lots of numerical tools handy that know how to do large dimensional integral, basically Monte Carlo. We don't do the whole integral, we just sample what are the important regions, right? Because there are going to be values of psi according to this weight that contribute almost nothing to the integral, so I'm not going to want to integrate over all those things. So we'll get there at the end, but ultimately this is amenable to Monte Carlo, where I weight my most probable field values by e to the minus action. Okay, and then the same thing for the gauge fields. This turns into just an ordinary integral. So my integral d psi bar, d psi, dA goes to product on X, I have to, so psi and psi bar are independent fields, so I have to integrate over each one independently. And then I have all of my lengths, and I should also go all directions with my length variables. All right, good. This thing we did last time. We talked about what happens to the action when we discretize it. A or U, whichever goes to. And I'm going to write this in a particular way, which will become clear why I do this in a bit. But these things turned into vectors. This thing is a scalar quantity, so I'm going to have to take these vectors and turn them into a scalar. This one we can actually think of like a row vector, and this one like a column vector. So our action is going to look like some matrix multiplication. So if I have psi of x here and x prime here, then this matrix connects x and x prime, and this gives me a scalar quantity, plus this thing that we derived last time that I'm not going to revisit, but I'm just going to call it SG. So now we're dealing with vectors and matrices. You can also write this in terms of vectors and matrices, and I'll write out explicitly what this matrix is based on what we did last time at the end of today. But why did I write it like this? So I want to calculate this ordinary integral. There's a complication. Actually, there are many complications. One complication is I said this is an ordinary integral, except that these psi fields are fermions. So what do we know about fermion fields? What must they obey? What? Antisymmetric, right? So if these were just values from minus infinity to infinity, I can't make them antisymmetric. Numbers are not antisymmetric. I could define these to be matrices and then integrate over all possible values of the matrices and then enforce that the matrices are anti-commutating. Yeah, maybe that's a word. That's really complicated. Lattice calculations are already very numerically intensive as it is. If we now call these things matrices, that makes it even worse. So the easy thing to do is to just integrate them out analytically and only sample the U fields, not the psi fields. So we don't know how to deal with these numerically, or we do, but it's super complicated. Maybe we can integrate them out analytically. And it turns out we can, because if you look at the fermion part of the action, it's quadratic in my fermion fields. This is e to the minus something that's quadratic. We know how to do quadratic Gaussian integrals. It's a little funny with anti-commuting fields, so I'll show how to do that. But it is something we can do analytically. All right, so who has learned about path integrals and integrating over Grassmann fields, antisymmetric fields. Did you all do that last week at all? Okay, good. Then what I'm going to say will not be a total waste of time for most of you. All right, we're going to go through it. So these things are anti-commuting. This means that the size anti-commute, the psi bars anti-commute with the size, and the psi bars anti-commute with themselves. Okay, so we're going to do the integral over these, but first let's do the path integral over this simpler case, which is a scalar field. So yes, this is an ordinary integral. It's a high-dimensional integral. And yes, it's going to be a bunch of Gaussians, but if you haven't seen this before, we're first going to do it with just scalars, and then we're going to go back and do it with anti-commuting fields and see that they're very similar. So let's say we have a path integral over some scalar, real scalar fields phi. So these do not anti-commute, they're just numbers. And we have an action that is quadratic in our phi's. So I call this B. So I have two phi's and a matrix multiplying it. Looks a lot like our fermion case. Okay, so how do we solve anything with a matrix? We diagonalize it, then it's easy. So let's assume that there is some orthogonal transformation that diagonalizes this matrix B. Then this thing just becomes a sum over the eigenvalues times phi squared. So this is the definition of diagonalizing it. If you don't believe me, plug this thing in up here. These are twiddles. No, those, yes, twiddles. Okay. These are the eigenvectors, the eigenvalues. Good. This thing should be a twiddle, but I chose an orthogonal transformation, so the Jacobian is 1. We don't have to worry about changing the integration measure. All right, e to the minus sum is the same as product of e's. So I'm going to pull the product. I already have a product out here, right? So I'm just going to write this sum as a product. There's an integral I'm forgetting. Here, here, great. Each one of these is just a Gaussian. So I have a product of many, many Gaussians. I know what the integral of a Gaussian is. It's the square root of, what, pi over something, something. So this is product on k, square root of pi over bk. And this is some constant, right? The product of root pi's, however many of those you have. We don't care about them because constants are always going to go away. We'll see when we calculate observables. It's a constant times what? What is the product of eigenvalues? A determinant, right? So it's the determinant of our matrix B to the minus 1/2. All right, so we've done our first path integral. And even when I take the limit, the continuum limit, where this is an actual path integral, this is what I get when I do a path integral over scalar fields. Okay. Anti-commuting fields, also called Grassmann fields. What is different there? They're actually almost easier because if psi anti-commutes with itself, what is psi squared? I think I hear the right answer. Yell it out. 0. Good. Right, because psi equals minus psi, and if psi is the same thing, this can only be true if psi is 0. It also means that the psi bars squared are 0. What about this? Is this 0? Yes? No? Oh, come on. 50-50 chance. I'm not asking you what it is, just is it 0? I mean, it might be. It's not obviously 0 because this can be true even if psi bar psi is not 0, because now psi and psi bar are two different things. So this is unique compared to this. So it might be 0, it might not be 0. Sometimes it's 0, we're integrating over all possibilities, but it's not necessarily. So this makes all of our functions of psi really, really easy. Any function of psi has to be linear because all higher powers of psi vanish. So we can write a generic function of psi as just a plus b psi. This is the most complicated function you can get. And in particular, an exponential of psi's you can expand, and you only have to go to linear order. It's not like last time where I was like, we'll expand it to linear order and higher orders are small because we have a small expansion parameter. No, it's exactly leading order for the case of anti-commuting fields. Okay. There is an important property of these fields, which is true in general for field theories, which is that they obey a shift symmetry. So if I shift psi to psi plus delta psi, my integral should not change. So what does that mean? That means that this guy goes to this, and a shift symmetry means that this is equal to the original thing, which, well, yeah, I wrote an arrow, but it's actually an equality. So what's changed? The constant term changed. it became something different. So if these two sides are equal to each other, the only way it can obey the shift symmetry is if the integral over the constant is 0, because it changed here. So it can only be that both this term and this term are 0. So that is tenet number 1. Where a is a constant. So now we've simplified our integrals even more. There is only one thing that can give you something non-zero when you're doing integrals over fermionic fields. This, if you have an integral over psi and 1 power of psi. This is the only integral that matters. And it's going to be equal to some constant times b. It's going to be a linear function of b. We don't care what that constant is. We're going to absorb it into our field definitions. It's going to cancel in our partition function. We never care about overall constants in our path integrals. So the convention is to just define this integral to be equal to b. We'll just say the constant is 1. So now you can do all fermionic integrals. They're super easy. What if I had a product of a bunch of psi's? We're going to have that as well. The only things that are non-zero, we have to have 1 power of psi for every integral over psi. So the only thing that would be non-zero would be if I had each psi that I'm integrating over appearing once. If any one of them is missing, you get 0. If you have an extra of any one of them, you get 0. Okay, there's one other ambiguity, which is even though we don't care about the constant, sometimes we do care about the sign because, right, we're insisting that these things anti-commute. So the sign has to matter. So if you have two integrals, d psi prime, the only thing that's non-zero is if I have 1 power of each appearing. And the question is this 1 or is the reverse order 1? The convention is that this has the positive sign. You do the inner integral first, and then the outer integral, and you get a plus sign. If I had this integral, first I'd have to swap them, then I can do the inner integral and the outer integral, and I get a minus sign. So that's the sign convention. And again, it's a convention because when you're talking about things anti-commuting, it's only the relative sign between the two different situations that matter. The overall sign is just absorbed into some constant. All right. So let's go back. Oh, good, I'm not erasing it. To our actual fermionic integral. So this was the fermionic part of the action. So let me just do a general Gaussian integral first. So here, these are, I just have two fields, psi and psi bar, and a constant b. I can expand this thing to linear order. And I'm done, because all higher orders are 0. This is an exact expression. We know that this term doesn't contribute. It gives us 0. That's the constant. Now, our ordering is wrong, though. We have psi bar appearing here, but we're integrating over psi here. So we need to swap them. That'll give us a minus sign. Psi bar. And I'm just going to pull b as just a constant here. It's not a matrix yet. So from this integral, I just get psi bar b. And then from this integral, I just get b. So similar to our Gaussian, except instead of root pi over a constant, we get the constant itself. So I can do the same thing I did before for a multidimensional integral. Now I have a matrix here, so I want to diagonalize it. These are now complex fields, so instead of an orthogonal transformation, it'll be a unitary transformation, but that's fine. Unitary transformations also don't change the Jacobian, so I'm free to do that. So I diagonalize it. And I get much what I had before. Just going to call these psi primes. I get the sum of my eigenvalues, psi bar prime, psi I prime. I turn e to the minus sum into product of e, pull the product out front. And now I just have a product of many of the same integral that I did up here. I know that each one just gives me the constant. So this guy is just the determinant. So instead of 1 over the square root of the determinant, for fermions, we get the determinant. It looks even less different than the scalar case. If in the scalar case, you looked at complex scalars, because then you have an integral over phi star and over phi. And you end up with 2 powers of this square root determinant. So had this been over complex scalars, we would have gotten 1 over the determinant of B. The fermionic case is exactly the same. You just put it upstairs instead of downstairs. And that comes from the anti-commuting nature of them. All right, so what have we done? What have we done? Okay. We have integrated out our fermion fields in our partition function. Remember that the partition function that I erased is the integral over Grassmann fields and the u's e to the minus the action. And we can split that action up to be e to the minus psi bar m psi e to the minus sg of u. This m in general depends on the gauge fields because the gauge field is in our Dirac operator. When we integrate that thing out, we end up with still the integral over our u fields. We haven't done that part yet. We get a determinant m of u and e to the minus sg of u. So now I've completely eliminated my fermion fields. I have just real scalar valued things, and I'm doing a high dimensional integral over them. And we can use a computer to do that. Now, however, instead of weighting everything by e to the minus action, this is our probability measure. This is the thing that we're going to use Monte Carlo methods, which I don't have time to go into, to sample. But if you think about, well, let me get there in a minute. Okay, we'll say that for now. All right, if you're doing finite temperature physics, then calculating the partition function is the thing to do. You would just calculate this thing, and then you'd take derivatives of it and do all kinds of other stuff. I am a nuclear physicist. I don't do finite temperature stuff. I'm interested in low temperature physics or zero temperature physics. So the kinds of things that I calculate are not going to be just the partition function itself. I want to calculate some observables, and typically we do correlation functions. This is the thing you learned in field theory that tells you stuff about the physics. So in our statistical mechanics language, what does that mean? It means I have some observable, some operator, O, that I want to calculate the expectation value of. And I do that by summing over all states, each weighted by their probability, and then dividing by the norm, which is the partition function. So same thing here. We have our partition function, it's this, and now we're going to stick some operators in it and calculate their expectation values. So typically, those operators are going to be some functions of our fields, because those are the only things that we have at our disposal in field theory. All right, so we still have to be able to integrate when we do this step. So now what I'm doing is I'm sticking in, I have some product of my integral over u. I'm going to call this thing rho of u. It's the probability measure of my integral. Oh, wait, hang on. Nope, I'm not there yet. I have my integral over my Grassmann fields. I have my operator, which is a function of my fields. And then e to the minus s, and I'm going to divide out by z, which is the partition, the same thing without the O in it. So we know how to do this, but how do we do this? because now my operator depends on fermion fields in general, so I have to now know how to do the integral, including this operator. But I already told you, fermionic integrals are easy. There's only one possible thing you can do with fermion fields. You can create one and annihilate one. That gives you a psi and a psi bar. Or you can create one and annihilate one at any site on your lattice, but those are the only things that can give you something non-zero. You can't have just powers of psi hanging around or just powers of psi bar, etc. So, Chuck. All right, let's look at an example. My simple example is that O is creating some fermion field at x2 and then annihilating it at x1. Physically, we know from perturbation theory that this has something to do with the probability of it propagating from x2 to x1. It's a propagator. We hope that we get the same thing coming out of this formalism. All right, here's where we get to the messy bits. So, we're just going to look at the numerator here because we already did the denominator. So we're on a lattice because it's the only thing that I understand. So these are now just field values at point x2 and x1. So it's like one element of my vector. And then the fermionic part, let's explicitly write in the sum over ij. Sometimes I assume that we're summing over doubly counted indices, and sometimes I don't. So please, if you're ever confused, yell at me. Okay, and then times stuff that depends on the use, right? So those are all just some constant in terms of our fermionic integrals. Okay. So what do? We diagonalize this thing using the same transformation we had before. We expand it to leading order. And, we diagonalize it, we turn the sum into the product, and then we expand it to leading order. So all the same steps there, I just have these things sitting out front. Okay, that's what I'm doing. So product on K, integral d psi K. And then this thing is 1. I'm going to write a plus sign because I'm going to go ahead and swap the fermions like we did before. We're now integrating over the psi primes. These two are at different points on our lattice, so they're not going to get the same, it's not the same element of u dotted into psi for each one, so the u's don't cancel. Let me write it, because those words, as I'm saying them, don't make sense to me. So the point being, we have to transform these psi's into psi primes, just like we did up here. But the u's are not going to go away like they did up here. We get a u dagger I did not leave myself enough space. Okay. U dagger, I pick out the x1 component. I'm applying this matrix to a vector P1. So this is the x1 component from up here. And then I need the x2 component from here, P2 prime U P2 x2, and I'm going to sum over P2 as well. So basically, I'm just rotating my size and my sidebars. In which one is daggered doesn't really make a difference. I don't know why I chose this one to be daggered. It really doesn't matter. All right, so this is the only difference from what I had before. And still, we only get something non-zero if every one of the size and every one of the sidebars appears in a given term. So, what can we say about that? So, this term, again, we're not going to care about because we only have we only have this particular psi and this particular psi bar, so all of the integrals over the other psis and psi bars will give us 0. Hang on, did I lie? I did lie, sorry. We have a product of these things. So we're going to have 1 times lots of other things of this factor. This is, like some polynomial of 1 plus x. So we have to figure out which term, when this whole thing is multiplied out, gives us something that's non-zero. So the only term that's going to give us something non-zero is if we have all of the psi bar size except psi p1 and psi p2 multiplying a 1. Right, so we're going to get all possible combinations of size. There's going to be one term where we have all of them except 1, and then that extra 1 coming from the thing out front. Let me write it. Sometimes math makes more sense than words. All right, so let me make one statement first, however. These guys always come in pairs with a repeated index. So there's going to be no term from expanding this out in which you have a psi bar that's different, a different index from your psi. So the only way we're going to multiply it by this thing and get something that gives us all powers is if P1 equals P2. We have to have a psi bar psi pair here multiplying all the other psi bar psi pairs in here. So I can go ahead and throw in a delta P1, P2. I'm summing over them, so I'm just going to set all of my P2s equal to P1. Okay, so that's step 1. So sum P1 actually, let me go ahead and pull my U's out front. So now I have U dagger X1, P1, U, P1, X2. So now this is just matrix multiplication. I'm multiplying U dagger U, and I'm taking the X1, X2 component of that matrix. Okay, and then, so I have my size here. This will give me one of the pairs, the pair where K equals P1. So I'm going to get a product of all M's except for M sub P1. So think about that for a second. The thing that has all powers of psi bar psi, it's going to have a psi P1, psi bar P1, product K not equal to P1, MK, psi bar K, psi K. So when I expand this thing out, there will be one such term, and that will be the only one that has all psi's represented. And we only get M's from the ones that come from this part of it, not from the one that comes from this part of it. All right. So, actually, I guess I could have, let's just do this. D psi, nope, it has to be inside. Integral D psi bar. Let's give it a different variable, L psi L, product on L. So all of my integrals, I've just picked out the one term that's non-zero, and it just gives me the constant. And that constant is U dagger X1 P1, U P1 X2, and then the product of these MKs. So it's almost a determinant. It's not quite a determinant. I'm going to turn it into a determinant by multiplying by MP1 and then also dividing by it. So now this thing is the product of all eigenvalues. This is the determinant. What is this thing? I've rotated it into a basis in which it's diagonal. I've taken a particular component and multiplied by 1 over the eigenvalue. Not quite. If I want to invert a matrix, what do? I diagonalize it. 1 over and then I just have the inverse of the eigenvalues. Here what I've done is I've picked one particular component. I've picked the x1, x2 component and multiplied by that eigenvalue. So, determinant, inverse. This whole thing integral d psi bar d psi this thing where I'm suppressing indices if we had, did I swap those? I did. This was x1, this was x2. Is the x1, x2 component of the inverse times the determinant. What is a particle propagator? I heard 1 over something. That's a good start. If I told you the action was this, be what? The inverse of this operator. That's what we know of as a propagator. Now, our operator is a matrix because we've turned our fields into vectors. And so the propagator is some component of the inverse of that matrix. And the partition function, the weights, are the determinant of that matrix. So we've taken field theory, which is this horrible path integral thing, and we've turned it into linear algebra, which is also how we do quantum mechanics, right? It's much easier when you learn that quantum mechanics is just linear algebra than when you're first learning the Schrodinger equation. And the things that we have to calculate, the things that computers are really, really good at calculating are determinants and inverses of matrices. Especially, and we're not going, let's see, did I at least, I will say 2 more things, but we'll get to next time what this matrix is. But remember, when we discretized the fermion action, basically we just took a derivative and turned it into a finite difference between adjacent sites. The indices, so what is the dimension of this matrix? Whatever the dimension of my space-time is, so let's say we have L cubed points on my lattice. It's in general L cubed by L cubed. Well, there's also time. We have to worry about time. Time is usually treated a little bit differently, but it's giant. However, these derivatives involve finite differences between adjacent points. So most of the elements of this matrix are 0, which means it's a very sparse matrix, and computers are also very good at handling sparse matrices. You don't have to worry about a fermion over here talking to a fermion over here. Well, you sort of do because there are gauge fields too. We'll talk about that a little bit, but still, this is very computationally intensive because these are huge matrices. So the job of a lattice theorist, I say there are roughly 3 different jobs of a lattice theorist, and they're often split up because the different things can be done totally independently. One is we've taken, let's say, some expectation value of this, and we've integrated out our fermions so that now we just have some high dimensional integral over our u's. We have a probability measure, which I wrote down over here, which is the determinant times an exponential. And then we have a propagator, which also depends on u. And I might be swapping my x1s and x2s, et cetera. So, job number one is to use Monte Carlo to sample the most important U configurations. So we call these field configurations, gauge field configurations. The most important ones are the ones that maximize that det m e to the minus sg. So, algorithms, fancy algorithms, they involve determinants, so you have to be able to compute determinants. It's very costly. But once you have a set of important gauge field configurations, you can use them to calculate any observable you want. So what does that do when we have, instead of an infinite number of field configurations, we just produce a finite set of the most important? That changes this integral into a sum, 1 over the number of configurations, that's this thing, that's the norm, sum of my important UIs, and then whatever my observable is on those UIs. So I compute the inverse of this matrix for each one of the U's that I've computed, and I sum them and I average them, and that's my observable. But if I have that set of U's, I can use any observable I want. So this step is carried out completely independently. Collaborations compute sets of gauge field configurations using their favorite discretization, different lattice actions. It's like having different experiments do the same thing. You want to make sure you get the same answer. And then they put them out there, and you can use them for whatever you want, depending on how generous they are. And you can calculate any number of observables. So step 2 is calculating observables on your set of field configurations. That's inverting a whole bunch of Dirac matrices. Step 3 is tying those things all together to give you the right quantum numbers and then doing analysis to extract information from it, which we'll talk about next time. I'm done.
Thank you. All right, do we have questions for Amy?
Hi, and thank you for the lecture. And I'm not sure if I understood very well why RK can't be equal to P1.
This step.
Yes.
Good. So, let's say we have 3 space-time points. I can do 3, right? It's probably easiest if we just do it explicitly. So, what we have is d psi bar 1, d psi bar 2, this. This. And then we have our U dagger U. I'm not going to write out the indices of that. And then let's say I have put my size, I create it at 1 and I destroy it at 2. And what order did I put them in? Okay, so I destroy it at 2 and I create it at 1. And then I have 1 plus M1 Okay, so this, I'm just writing everything out in terms of my 3 integration variables, or 6, technically, psi 1 bar, et cetera. All right. Now, hang on. Nope. So we converted to momentum space rather than position space. So if I start out with two things at different points in position space, when I Fourier transform, I find that the momentum has to be conserved. But you can see that here if I just give them arbitrary indices. Let's say I create one at j and I annihilate one at I, and these are totally arbitrary. We're going to see that almost all of them don't contribute. So the only thing that gives me a non-zero integral is if I have a psi bar 1, psi bar 2, psi bar 3, psi 1, psi 2, psi 3. Right? This is what we got from our Grassmann integration. So we're going to have terms that are 1 times 2 of these things, or 1 times 1 of these things, or all 3 of them. The one where I have all 3 of them can't work because I have an extra psi bar psi out here. So that's going to give me 0. The terms where I have a 1 and then 2 products of this could give me something non-zero. And finally, the terms that are 1, 1, and 1 product of these can't work because then I have only 2 pairs, not all 3. And I need all 3. So the only contributions are when I have a 1 times 2 of the other not 1 terms. So first I claim I has to be equal to j. That's because these are all pairs. So if I have 2 of the pairs, the other one has to be the third remaining pair. So that only works if these 2 are the same, because these don't have any cross terms in them. Okay, so now I can just say, well, what if I just call it 1? Then the term that survives is this times 1 times this times this. So here I have psi bar psi 1, psi bar psi 2, psi bar psi 3. So I have 1 times m2 times m3. So that's what the product of k not equal to p1 is. It's the product of all the ones that aren't the 1 in your operator. And I can play the same game if I had 2, 2 here, then I would have 1, 1, and 3, 3. So the one that's missing is always the one in your operator that's going to not contribute an m. Good?
Okay,
Yep.
thank you very much.
Mm-hmm. Yeah, it's a lot easier if you just write it out. It's harder for me to wave my hands.
Hi, thanks. I know that Lattice QCD have the sign problem, and there is some way that I can see that in this, I don't know, at this lecture level, or I need to have a chemical potential.
Yeah, so the sign problem comes in when you add a chemical potential to the theory. If you have no chemical potential, this determinant is positive definite, depending on the number of flavors in your theory. It's positive definite if you have U and D as degenerate quarks, then you basically, for every flavor, you get a determinant. And if you have degenerate quarks, then you have 2 powers of the determinant, and it's positive, yay. If they're not degenerate, it's almost positive, so you can play games with it. But when you add a chemical potential, then you get an imaginary component. And that's what gives you the sign problem. Mm-hmm. Let's see, can I show it quickly now? We have a couple minutes. So what happens when you add a chemical potential? So your operator this matrix that I had before is this plus, oh no, it's already in there, right? The gauge field is in here. It's the discretized version of this, which we talked about last time. And the way you can show that M is positive definite, that determinant of M is positive definite, is because it obeys what's called gamma 5 hermiticity. So a determinant of a matrix, determinants are cyclic. Gamma 5 squared is 1. So I can stick in gamma 5 squared here and then cyclically bring it to the other side. And this thing, so if you put in gamma 5s here, there's a gamma 0 in here, so it anti-commutes with it. I think there's an I here, that's important. So when I move it through and cancel it with the other gamma 5, I pick up a minus sign. So that takes I to minus I. So this is det M dagger. So let's see. What am I missing here? So it also, yeah, so somehow you say that this is equal to det M. I'm missing a step. Oh, yeah. Step 1 was that this is det M, right? I said that this is det M. I multiplied by gamma 5 squared. I moved it through. And then that's equal to det M dagger. So this thing is positive definite. Good. When you add a chemical potential, that chemical potential couples to baryon number. And baryon number has a gamma 0 in here. So it's plus I mu psi bar gamma 0 psi. This gamma 0 destroys the gamma 5 hermiticity, and you can no longer say it's positive definite.
Thank you very much.
Sure.
Hi. About the shift symmetry that you mentioned, why can we assume that we have that symmetry?
So it's a property of all field theories because the observables we're interested in don't care about constants. So like, oh, I'm going to say words and wave my hands because I don't want to do math, but so, okay, yeah. When we talk about quantum field theories or quantum theories in general, right, everything comes from the Hamiltonian that tells us the spectrum of the theory, et cetera. And if we add some constant to the Hamiltonian, that's just shifting all values of the fields. And it always cancels in your partition function. So when you divide by your partition function, any constant shift that you have will go away. It's not anything that comes into the physical observable. I don't know if that was a good explanation or not, but.
Another question over here.
Hello, thanks. I know that for the baryonic chemical potential, we always have the sign problem. And in some cases, the isospin chemical potential, we don't have sign problem.
In some case, what? I'm sorry?
For the isospin chemical potential,
chemical potential, yeah.
What happens in this case?
Yeah, so if you have an isospin chemical potential, you're also putting in a tau 3 here. So this tau 3 acts on the flavors. So now this guy you think of as a vector. This counts the number of U's minus the number of D's, which is what isospin chemical potential is. And now so you no longer have gamma 5 hermeticity, but you have something, you can do like gamma 5, maybe it's gamma 5 tau 3 M. I don't remember exactly what it is, but you have a slightly different symmetry that comes from the fact that U and D are identical, and you just get an extra Pauli matrix in here. So it's like a simultaneous counting the number of left-handeds minus right-handeds plus ups minus downs. Those combine to give you something that is positive definite. Yeah, and another way to think about it is when you put in a baryon chemical potential, you are favoring baryons over antibaryons. So that's like computing some expectation value where you have some number of baryons in it. This thing is clearly not positive definite because if its dagger is the bar. But if you put in an isospin chemical potential, you're creating a bunch of pions in your vacuum. And pions look something like psi dagger psi. And this operator you can show is positive definite. So those are related. The correlation function, we'll talk about signal to noise, but there's a signal to noise problem with the fact that baryon operators are not positive definite, but pion operators are.
Thanks a lot.
Hi, Anne.
Hi.
Thanks for the lecture
Sure.
again. I have a naive and quickly question. Are you using Lattice QCD with finite temperature? Is possible to use the lattice to compute some physical quantities with zero temperature?
Okay, so I heard if you're using finite temperature lattice QCD, what was the rest of that?
If it's possible to compute some quantities, physical quantities, with zero temperature with lattice. I don't know if it makes sense.
Yes, so everything that I do is zero temperature. So zero temperature is just taking the long time limit. And I'll show next time that these correlation functions that we've computed can give us zero temperature quantities.
Okay.
Yeah,
Thank you.
exactly.
Hi.
Hi.
I have one question. So when we are calculating this correlation function, so what's the role of lattice spacing? Because I don't see lattice spacing there.
Yeah, so
are they dependent on lattice spacing? What lattice space we choose?
So the lattice spacing is going to come into the definition of this M. So normally when you write an action, it's the integral d4x of the Lagrange density, right? The discretized version is going to become, so if we discretize an integral, we multiply by the size of our partition, and then we sum over sites. And this is going to be psi and u and all those other things. So there's going to be a lattice spacing that comes into the action, for sure. We also had, I think, 4 powers of A when we wrote down the gauge action. The path integral itself, probably there are powers of A, but they're going to cancel when you divide by the partition function, so we don't worry about it. Lattice theorists are super lazy, and just like particle theorists, we use units where everything is 1, so we don't have to worry about them. So if you don't see powers of the lattice spacing, it's because we've said A is 1, and we're just counting the number of sites. So if you want to go back and put in the physical A in terms of Fermi or something like that, you figure out what is the energy dimension or the mass dimension of the thing, and then you multiply by the appropriate powers of A to give you whatever dimension you're supposed to have. So like an action is supposed to be dimensionless because it's up in an exponent. So if I don't put factors of A in here, all you have to do is figure out what is the mass dimension of this thing, and then multiply by that number of A's, and that gives you something dimensionless.
Okay. And one small question related to the total action. So it's erased, but we have this exponential minus this term, right? And like we are moving from Gaussian space to the Euclidean space. So it's implicitly dependent in some calculation, or we do it just to do the Monte Carlo?
You mean the time?
Yeah, just when you go from imaginary time to real time.
Yeah, so I will also show this next time, but in a Minkowski path integral, you don't have e to the minus s, you have e to the is. Taking t to minus it gets rid of this I and makes it some real valued thing. So why do we do it? Well, one thing, we can't calculate a very large dimensional integral. We have to use Monte Carlo. Monte Carlo relies on you having configurations that are weighted according to their probability. So it has to have a probability measure, and if this thing was complex, it wouldn't make sense, right? You can't have a complex probability measure because it has to norm to 1, and you can only have positive probabilities. So it makes our probability measure positive. We can use Monte Carlo. People would love to do Minkowski space calculations, but then you need to actually explicitly do these integrals and not do Monte Carlo, and that's what quantum computing wants to do. Things like that. So they put it in terms of a Hamiltonian and into real time and actually do the full quantum mechanical thing using qubits.
All right. So thank you, everyone, and thank you, Amy. We are on lunch break now. When we come back at 2 p.m., Andre will be giving the IFT lecture or colloquium in this room. Afterwards, during the coffee break, there's also